Well, hello and welcome again to our journey into complex analysis. And in section 10 we're going to look at Laurent series. We have looked at infinite series in the previous sections and in Taylor series, and now we get to this new sort of series called a Laurent series. To motivate it, I just start off with a very simple function. F of z is e to the z on z squared, and clearly you can't get a Taylor series for this about z equals naught because f of naught's not defined. However, if we pretend take z not to be 0 for the moment, and just look at the e to the z on the top, then I can expand e to the z out as a Taylor series, and there it is. And then I can divide the 1 on z squared in, and I end up with a new sort of series, which is not valid at 0, but the step from e to the z to the infinite series is valid for all other z. So this is going to converge for all z, except we've got some problems at 0. But it's a new sort of series because we now have z's not only in the numerator up here, but we're going to have them in the denominator as well. And this series is an example of what we're going to call a Laurent series. So definition is a Laurent series for f is a series of the form, we have some, this is about the point z naught, so we've got some coefficients times z minus z naught to the n, but this time our n can range from minus infinity up to plus infinity. We'll see that some Laurent series are like this. They've only got a few terms at the beginning with z's in the denominator. Other ones we will see are double-ended. They have infinitely many terms with the z's in the denominator and infinitely many with the z's in the numerator. So the Laurent series is defined by that, and we say it converges if both the positive series, if you will, the terms with the z minus z naughts in the numerator, and the terms with the z naughts in the denominator, z minus z naughts in the denominator, if they both converge then at z, then we will say that the sum of these converges and it's the sum of the two series. So the main theorem, Laurent's theorem, tells us that if we have f is analytic on an open set omega containing an annulus where centre z naught and the inner and outer radii are R1 and R2, and so we've got a picture like this down here, and we let gamma 1, gamma 2 denote positively oriented inner and outer boundaries of the annulus. So there's my gamma 2 is the outer, and this gamma 1 is the inner. Then if I'm in the annulus, provided I'm inside this annulus, then this f has a convergent Laurent series. Moreover, we can explicitly write down what the coefficients are. The positive coefficients, the a sub n's for n bigger or equal to 0, are given by this expression, which again is looking remarkably like generalized Cauchy integral formula, and we'll see that's where it comes from. And the a sub minus n's are given by this, which is very similar again, except obviously we're just replacing n with minus n. Now in practice, we don't use these formulae in general to work out the coefficients here. We're going to use our standard manipulation of known series, so this is a theoretical result. So here's the proof of this. So if we're inside the annulus, this bit here, then we can take the path going along gamma 2, and we use this bridge idea. So we go in here, we go minus gamma 2, so we go in that direction, and then we use the bridge to get back out again and finish off the gamma 2, and that will enclose this annulus. And in that case then, we can write that we can take this f of z, and we can write this as, using Cauchy integral formula, we can write it as the integral of this integral along gamma 2 minus the integral along gamma 1. I'm going to label these ones, this is function f2 of z along gamma 2 and f1z on gamma 1. Now what we need to show is that these converge and that the coefficients are given by these two expressions up here. Now our f2 was equal to 1 over 2 pi I, integral f of w on w minus z. So z, remember, is a point inside the annulus. This will have a power series expansion inside the disk, inside the big disk, centre z0, radius r2. So if it's got a power series expansion, then I can write it like this, and the coefficients of this, the a sub n's, then, this is just a Taylor series, so that they are given by, just from ordinary standard calculus, these are given by the nth derivative at z0 on n factorial. But then this, of course, is just equal to this expression by the generalized Cauchy integral formula. And so that's where those coefficients come from. Now, on the other hand, if we take f1 of z, then that was the minus the integral along gamma 1. And this time we're looking on the outside of the disk, so for z minus z0 bigger than r1. Now we can just do a little bit of reorganizing here. I can rewrite this integrand in this way. If you just multiply it out, you'll see you get z minus z0 minus w plus z0, which is z minus w, which is minus this. So the minus there has been used to turn this around, and then I can factor out a z minus z0. And this thing in here, this is the sum of a geometric series, so I can expand this out as a geometric series, and I can write this as this. I can write the integrand here as this sum. Now it's not hard to show, this is just using geometric series, it's not hard to show that by Weierstrass M-test this series converges absolutely and uniformly, so we can interchange the integral and the summation sign. So we're going to then get the sum of 1 over 2 pi integral of this expression, and this thing here is simply going to be some series of this form, and the coefficients, we can read off from here what the coefficients look like, and that's the formula we had from before. So we see that both f2 of z and f1 of z converge, and the coefficients are given respectively by these two integrals. As I mentioned before, in practice we rarely use these integral formulae. They're good for theoretical, they've got lots of theoretical uses, but to actually find the coefficients we're going to manipulate known series. And I'll just do an example of this one here. We take the function 1 over z minus 1, z minus 2. We want to find all the annuli in which f has a convergent series in powers of z minus I, and we want to find the corresponding series. So here's the worked example for this one. So here's our function. F of z is 1 on z minus 1, and we want it in powers of z minus I. This is telling us that our annuli will have centre I. So I draw a little picture up in the complex plane. There's the annulus centre I. And now we have to find the circles. We have to look now at the singularity. So f has a singularity at 1 and 2. So you put little x's to mark the singularities. Now you're standing at the point I, and I like to think of it as you're swinging your lasso, your piece of rope, and you let it out until you're just about to hit the first singularity. So we know there'll be a Taylor series that's valid inside here. Well, then you forget about this one for the minute and you continue letting out your rope, and you stop just before you're about to hit the next singularity, so you swing your lasso around, and that'll be at 2. And so we know also that there's going to be a Laurent series that's valid inside of this disk here, this annulus here. Now, if we think about the outside is also an annulus, except the bounding circle is at infinity. So you can think of there being, in fact, 3 regions here. So this little picture shows us that the singularities and the centre split up the plane into 3 bits. In region 1, there'll be a perfectly good Taylor series. In region 2, there'll be a Laurent series. In region 3, there'll be another Laurent series where the bounding circle of the outer annulus is the circle at infinity. Okay, so to do all the hard slog on this, we now use partial fractions just to split this up, which is easy. You can do it by inspection. And we want everything in powers of z minus I. So I immediately replace z with z minus I, and then I better patch it up. So I better add I there, and I subtract I and add I there. Now inside this first region, we want this will be a Taylor series, and that will be valid inside of this disk. So that'll be valid, the radius of this of course is root 2, so this will be valid for mod z minus I less than root 2. In region 2, we're going to be outside of that circle but inside the big circle, and you can see Pythagoras tells you the radius of that's root 5, and the outer Laurent series will be outside of that circle. So in region 1, we want Taylor series, so we just do it as we would have before by using Taylor series. We factor out the constant. As a general rule of thumb, if you want a Taylor series in these sort of rational function situations, you factor out the constant terms. So I do that, I get this here into 1 plus z minus I and I minus 2, and then minus, I factor out the constant term and I get this. And now we use our known series, we can expand this out as a geometric series, as we did in the proof in fact. And we end up with this expression, and I expand this out as a geometric series, so we end up with this expression. And now you can combine these together, so it's sum n bigger or equal to 0 minus 1 to the nz to the n, and the coefficients are given by this expression in here. Now you can check where it's valid. It's valid where the modulus of the common ratio of each of these common ratios is less than 1. Yep, so because they're geometric series, they will only be valid when the common ratio has modulus less than 1. This one gives you root 5, this one gives you root 2, so you want to be inside a disk radius root 5 and inside a disk radius root 2, that is, you want to be inside a disk radius root 2. Now for the second region, we notice that this first function here has its singularity at 2. So if I want a series that's valid inside this annulus, then in particular I want to be inside the disk for this one. So this will have a Taylor series again that's valid everywhere inside the disk. This one has the singularity at 1, and so I want a series that's valid outside of this circle. So again, I use that sort of rule of thumb. If I want to get a Taylor series, you factor out the constant term, which I've done here. And if you want a Laurent series that converges outside of the disk, you factor out the terms with the z's in it. In other words, back up here, I factor out this one for the Taylor series, and I factor out this one to get the series converging outside of the disk. So I'll grind through the calculations here, so I factored that out there, and then once again you expand these out using known series. This is our geometric series. Now again, these expansions will be valid when the modulus of the common ratio is less than 1. So I want the modulus of that less than 1 and the modulus of that less than 1. Well, this one gives you z minus I is less than the modulus of I minus 2 is root 5. And this gives you, if you split it up and take the modulus here, you get the modulus of z minus I is bigger than the modulus of I minus 1, which is root 2. Now that's exactly where we want to be. That's the annulus between the two circles. Finally, we can do the same thing for the third one. This time we factor out the z terms in both and expand them out as geometric series as usual, and this time we want the modulus of the common ratio has to be less than 1, and the only place where both of those are satisfied is that mod z minus I is bigger than root 5. So that's just an example there. There's another little challenge problem. You can try repeating this exercise for this function. Now we've got a square here, and my hint here is do not work out a series and square it. My suggestion here is to you split this up using partial fractions, and then to get the series for the square bit, work out the series for 1 on, or something, whatever it is, on z minus 2, and then differentiate, and that'll give you a term here. So that's a nice exercise to grind through. Sometimes we're happy with just knowing a few terms of the series. So for example, if we want the series z minus 3 times the sine of 1 on z plus 2 about z equals minus 2, notice that's going to be a singularity here. So sometimes we're happy with just that. And let me just do the worked example of that then. So here it is here. So there's our function, and we want it about z minus 2. So we firstly have to take this z minus 3 is a bit of a pest, so I need to write this as z. I want everything in powers of z plus 2 if I'm expanding about minus 2. So I'm going to write z plus 2 here, and then I've got to patch it up by subtracting 5 times that. Now this one then is z plus 2 times the sine expansion, and we know the series for sine, so I just replace z with 1 over z plus 2 in. I can write the first few terms of that down, and then I've got minus 5 times the same thing. And now I just take out the brackets and simplify a little bit as best I can, so I get 1 minus 5 on z plus 2 minus 1 on 3 factorial z plus 2 squared, and so on. And you can, if you want to, write down a general formula for this, but I just wanted the first few terms of it. By the way, in this particular case, this z plus 2 is going to occur infinitely often in the denominator. And we're going to see later that such a singularity is going to be called an essential singularity. I should mention also that the principal part of a Laurent series are the bits with the z's in the denominator. So the principal part of this function would be this much without the 1 there. Okay, well, and I mentioned that in the next thing here. So that part of the Laurent series which is given by the sum from minus infinity to minus 1, that's called the principal part of the Laurent series. Well, little challenge problem to play with. This is rather sweet. If you look at f of z as e to the 1 over z, and you write down the Laurent series for this in powers of z, that's very easy. You can then use Cauchy integral formula for the coefficients. Here's where we are going to use those formulae I mentioned before for the coefficients, and you can deduce this rather amazing looking integral, the integral 0 to pi of e to the cos theta times the cos of sine theta minus n theta d theta is pi on n factorial. It's a rather remarkable integral. I'm not sure how you would do that without using complex analysis. So in the next recording we'll have a look at the connection between Laurent series and integration, and we're going to then come to a rather remarkable fact which tells us how to work out all complex integrals in some sense using what are called the residues. And this will give some reason as to why we wanted to study these Laurent series in the first place.